Welcome to Demystifying Math. In this lesson, we're going to be graphing a rational function. Specifically, we're going to graph a function that has a hole in the graph. We're going to look at the function f of x equals x plus 2 over x squared minus 4. Before we start trying to graph it, let's first look at the domain of the function. We can identify the domain by factoring out the denominator, which factors into x plus 2 times x minus 2. Which tells us that if we put a 2 or negative 2 in for x, our denominator will be 0 and the function will be undefined. So our domain excludes negative 2 and 2. In our interval notation, we have an interval of negative infinity to negative 2, and then we have another interval starting at negative 2 and running to positive 2, and our third interval runs from 2 to infinity. We're using the soft brackets to show that negative 2 and 2 are excluded from the domain, so they are not endpoints of that interval. Whenever you have an undefined value for your function, you want to check and see what happens to the graph as x approaches that undefined value. So in this case, we want to see what happens to our graph as x approaches negative 2. We're going to start on the left side of negative 2 at negative 2.1. So I plug negative 2.1 into the function and my output value was negative 0.2439. At negative 2.01 I have negative 0.2494. And at negative 2.001 I have negative 0.2499, which is very close to negative 0.25 or negative 1/4. And all those numbers seem to be approaching negative 1/4. Of course, at negative 2, it's going to be undefined. Let's look and see what happens on the other side of negative 2. So for coming in from the right, starting at negative 1.9, I have negative 0.2564, which is a little bit above negative 1/4. At negative 1.99, I'm a little bit closer to negative 1/4. And at negative 1.999, I'm very close to negative 1/4. So on that side, the graph seems to be approaching a negative 1/4 as well. So what we can say is that as x approaches negative 2, y approaches negative 0.25. Now we could have found that out by looking at the simplified version of the function. So if you go back to the original function here where we had x plus 2 over x plus 2 times x minus 2, these x plus 2's cancel out, and we're left with 1 over x minus 2. Now if I take that simplified form of the function and I plug in negative 2, I get out negative 1/4, which is what we found as what happens to the original graph as x approaches negative 2. The two functions that we have, the x plus 2 over x squared minus 4 and the 1 over x minus 2, are similar graphs. They will behave in exactly the same fashion for every single point of x except at x equals negative 2. That's the point at which the original graph is undefined, but the simplified version is defined. So instead of having an asymptote as we normally expect to have at undefined values, we simply have a hole in the graph at the point negative 2 and negative 1/4. Now we had another undefined value at positive 2, so we want to see what happens to our graph as we approach positive 2. So I picked a few numbers very close to 2. So starting at 1.9, my output is negative 10. At positive 1.99, I have negative 100. And then at 1.999, I have negative 1,000. And if I go in a little bit closer to 2, I have negative 10,000 for 1.9999. So these numbers seem to be approaching negative infinity. So we can say that the graph is heading to negative infinity as x approaches 2 from the left. Notice this is kind of different from what we just saw, because on the previous one we were heading toward a specific number. Here we're just getting larger and larger and larger. Let's see what happens to the graph as x approaches 2 from the right side. So at 2.1 we have 10, 2.01 we have 100, then 1,000, and 10,000. So these numbers are approaching positive infinity. So as x approaches 2 from the right, the graph is heading to positive infinity. Remember that if you have a graph that's approaching infinity or negative infinity, as x approaches a specific number, then the graph will have an asymptote at that point. So we're going to have an asymptote at the line x equals 2. That's going to give us our vertical asymptote. Okay, so the next thing that we want to do is find our horizontal asymptote. So for that, we want to see what happens to x, what happens to the graph as x approaches infinity. So we're going to start at 10, and we have 0.125, 100, 0.0102, 1,000, 0.001, and at 10,000, even smaller. So these numbers are heading towards 0. So we would say that y equals 0 is the asymptote. Now there is an algebraic way for you to figure out where the horizontal asymptote is. What we can do is take our original function and divide everything by x squared. You always want to divide by your highest degree variable, and do that to each and every term so that you maintain the equality or the ratio that you have for your fraction. And then simplify each one of those. So where we had x over x squared, I got 1 over x. And where I had x squared over x squared, I rewrote it as 1. Now you want to see what happens to the function as x goes to infinity. Well, as x gets infinitely large, let's say that x was a huge number like 10,000. If you had 1 over 10,000, you would know that that number is going to be really close to 0. If you had 2 over 10,000 squared, that would be even smaller, closer to 0. And the same with 4 over x squared. So these three terms here are heading towards 0 as x approaches infinity. As x approaches infinity, 1, which doesn't have a variable with it, is going to stay at 1. So we would say as x approaches infinity, the function f of x approaches 0 plus 0 over 1 minus 0, which is 0. Which means that f of x equals 0 is an asymptote, or y equals 0 is the asymptote, and that'll be our horizontal asymptote. Okay, so now we're ready to draw a graph. We have the two asymptotes, we have a hole in the graph, and we're going to plot those and draw our lines. So these will give us boundary lines for the branches of our graph. And we have the point at -2, -1/4 plotted as an open circle. Now what we want to do is plot a few more points and connect with smooth curves. Since these two functions, the x plus 2 over x squared minus 4 and the 1 over x minus 2, are the same graph at every point except where we have the hole in the graph, we could plug our values of x into the simplified form of the function and get out the same values. So for instance, if we plugged in a 3, we would have 1 over 3 minus 2, which gives us out 1. So that gives us that ordered pair at 3, 1. And I did the same thing for the other ones. And now you can see how the smooth curve fits with all the information that we found. So as x goes into 2, from the right, it's heading up to positive infinity. As we go into 2 from the left, it's going down to negative infinity. As we go out to positive infinity for x, our y values are coming in closer and closer to the x-axis, or y equals 0. And the same thing, even though we didn't test it, it's on the negative side. As x goes to negative infinity, the graph is coming up towards 0. Now, here at this open circle point, you can see that our points are coming in close to -1/4 for the y value from both sides. So you have this point here not being an asymptote because it's not heading off to infinity or negative infinity. It's actually just coming right into that point there. Okay, thank you for tuning in to Demystifying Math.